Hello, Phil.
Hello, Andre. Nice to see you.
Good seeing you. We know each other for quite a while, and this is actually a wonderful opportunity for us to have a little bit of chat and go over some of the fun science and microscopy thing. So I'm really looking forward for this.
Yeah. Well, I have to say that the experience so far has been fun most of the time, and hopefully that's the impression that will get taken away from this interview.
Wonderful. So I have so many questions for you, but I would like to go with a little bit historical background and with a little bit start from very beginning. So what made you be interested in science? So do you have some early memories from childhood and from early days of your education so that you find that, oh, science is fun, let's do it?
Well, this happened very early for me, but I think it was as I think back on it, I was growing. My early years of growing were right in the middle of the explosion of electronics and in radio and television, and so there were these amazing boxes that did interesting things that I didn't know how it worked. So one instance I remember is sending away using the serial box top for a crystal radio, and it arrived, and it was about 2 inches long by about an inch square. So I put the earphone in, and I clipped the ground clip to a pipe that went into the floor of the house, and I was sitting there on the floor tuning it, and something startled me. I don't remember what it was, but I jerked my head, and the radio came apart, and what looked like a pencil fell onto the floor. And as I was watching it hit the floor, it morphed. It really changed what I could perceive from a pencil to a little tube with wire wrapped around it. And I remember that very clearly, and the joy that it gave me to say, hey, there's something inside there that's important.
Oh, that's a fun story. And then those was one of the moments you feel like, oh, this is good. I would like to pursue understanding the world around it.
Well, it was part of, I think, just a real curiosity that I still have about how things work, and to the extent that involves building machines or taking machines apart. Or I have one story that I wrote in my English 135 freshman seminar, talking about being home on vacation and sitting happily in my bedroom, ripping apart a hapless radio. So it's part of what I am. Maybe, and that's really all. I could go on for hours about it, and of course we don't have the time, so I won't do that.
Well, maybe another day we'll go a lot longer about that. So now, could you please tell us what happened? So that I think later on you went for a college, and I think you went to the undergraduate and do the undergraduate and graduate studies at Cornell. So want to share some of the early stories about the more formal education?
Yeah, the whole period of time was, I don't remember any down periods. I remember it all as being joyful. It was hard, doing determinants to solve for currents in a double E electrical engineering project. That was hard, but but everything that I did, I had fun with. And right, and the professors and the section managers, they responded to that fun that I had. And it was, I don't remember a downside. Even when I walked into for a final exam once in engineering drawing, and I had got the time wrong and overslept. And they said, don't worry about it. You take the next section. And so they all just laughed and we had fun.
Oh, that sounds of a fun time.
I was very lucky. I was very lucky, yes.
How about your experience in a grad school? And actually, just to mention for everybody who is listening, Phil and me, we had both same advisor, Professor John Silcox in applied physics at Cornell. So, but I was there a little bit a later time, and you're there from early days of especially electron energy loss spectroscopy used with the TEM. What was your experience first encountering the TEM as a scientific instrument, and then even further and doing electron energy loss spectroscopy, which we often refer as EELS?
Yeah, so I should preface this a little bit because my time at Cornell was unusual. I was both an undergraduate and a graduate there. So I had 10 years up in Ithaca. And John Silcox was my undergraduate advisor. I walked into his office as a sophomore in 1967, unbelievably. And John may have had his eye on me. He may have had figured out that I enjoyed, taking stuff apart and doing stuff with it because he encouraged me to take part in the co-op program as an undergraduate. And that put me in the middle of a tech firm in Nashua, New Hampshire. And so I got a look at what doing engineering science, engineering physics in my case, meant for a career. So then when I got to be a senior, I had a ready opportunity at Cornell. I did look around at other places, but Cornell seemed to be just the right place for me. And John had a project that was perfect because it involved interfacing a PDP-11 to a 20-year-old electron microscope so that instead of taking data with electron image plates, we could take data digitally and get a data set which we could then process to create a data set which was familiar to the theory community, especially in physics, so that they could run with it. So that's a really big chunk of description there. If you want to ask about details along the way, I'll be happy to elaborate.
And the data you are referring here is both images and EELS data?
Yes, well, it was image data as a function of energy and scattering angle. And the physics community had a really hard time understanding this because at the time you couldn't publish photographs in PhysRev letters. They didn't have the capability to do that. And they didn't understand what it meant to say, this is intensity as a function of energy loss and scattering angle. My lab co-student, Sunshine Chen, had that trouble when he tried to publish his stuff, because we see intensity that creates a dispersion relation that's right there in 2 dimensions. And so part of what was hard about what we were doing was making plain to the physical science community that electron microscopy electron energy loss spectroscopy could be hard data and not simply images, not simply pictures.
Now, how was the experience of converting images into the digital data?
That was fun. It required some construction. It required me to understand how to deal with high voltage. There was the one day that I pulled out the hot 75 kilovolt plug and lived. There was the day that the guts of the tank fell into the oil and drenched me. But I learned how to nail down the details so that what you presented, again, for people who don't know the technique very well, to present the data in a way that is useful to them. I learned that early.
I guess it took quite some time to get this all sorted, and then John Silcox was patient enough to let you to do all of the fun.
He did poke at me. He wanted to know when I was going to stop building equipment and start taking data. And I had my back up against the wall. And I remember thinking it, but I don't know whether I said it to him, that John, you can't do this stuff without getting the details right. And eventually I did manage to get the data.
Well, and your interest of the tinkering with the equipment was even present then, I guess.
Well, it was tough. You know, if you wanted to, this was the plasmon dispersion data was at root a three-dimensional data set. And I used a polycrystalline sample so that one of those dimensions went away. So I had a two-dimensional section of a cylinder. And then so I had 32 scattering angles and 256 energy pixels. And I needed to do a two-dimensional Fourier transform that was actually three-dimensional. So I needed to do the transform in the angular direction as Bessel functions. So, and this was on a PDP-11 with a 1 megabyte disk drive and 15 kilobytes of memory. So you can imagine the hoops that we had to jump through in order to get that done in a sensible way.
Probably for our younger viewers, that will be quite shocking at what type of computers were available at that time, and you still need to manage to get it work. So that probably was a interesting time.
I learned a lot of details about about what's behind the box in order to do that, and that served me well later in my career.
So in this exercise, it looks like you also need a good understanding of computers and how the computers interfacing with the microscope. Want to tell a little bit about that? How you managed to get those things sorted?
Well, I think the computer, the PDP-11 came with a digital interface. So there were a set of directions. There was a kind of an orphan IBM Selectric from the closet that I reverse engineered and plugged into the machine so I could type my thesis. But to not get off the track, I think the co-op experience was helped me with that, because I remember being aware of the details of the software at the assembly language level. You know, what it meant to have an interrupt and a return from interrupt, and those kind of things that you really don't want to have to do. So remind me if I'm not answering as much as you'd like.
No, this is all good. And apparently that time for you appears to be very productive, because I still have a copy from your of your papers from the graduate school year. So they are really good. I like reading them. So, and let's kind of go to the next stage of your development. So I think you took a postdoc position in Europe, right? After PhD. So will you share with us a little bit about your postdoc experience?
Yeah, I got really lucky. My wife had a fellowship to go and study abroad, and so I was busy hunting. And Archie Howie visited Cornell from Cambridge, and so we got to know each other, and he knew that there was an opportunity that actually was out of Glasgow University. And their interest was in differential phase contrast in magnetic materials. So this would be a split detector. So you make a small displacement on the detector, and that gives you a phase shift, and you can get in focus imaging of magnetic fields. And they had money for a postdoc in Cambridge at the Cavendish. So I spent 2 amazing years there, being careful not to be killed on the highway riding a bicycle on the wrong side, and making new friends with entirely different backgrounds that remain true to us today.
Were you located at Cambridge or Glasgow?
I was located in Cambridge. I visited Glasgow to get caught up with the way the project was going. And John Chapman, who was the PI, came down to Cambridge for 2 or 3 days at a time. They were kind of hectic because the first, you only had, say, 3 days on the machine. You had to get the detector, you had to let the machine up to air, put the detector on the top, and get it pumped down and functioning, and then figure out what you're after. So 3 days, you had 3 days. So your first day was a dead loss, and you went home depressed. The second day, you'd sort of see something that looked interesting. And the third day, you get a complete data set, and John would go away happy.
Nice. And what type of instrument was available at the Cavendish? So
these were the first scanning transmission electron microscope. So this was a VG microscope. The idea really derived from Crew's work in Chicago for a lower voltage system, but it was a scanning system as well. And the one in Cambridge was, I think, the second one that VG built. So they were roughly 100 kilovolt machines with a field emission source in ultra high vacuum at the bottom, and a very simple 3-lens system to create a probe size of about 5 angstroms, which was very good in those days, and a scanning system, and then detectors in the far field after the specimen without any optics in between. And we learned how to do annular dark field imaging, and with a spectrometer on a magnetic sector spectrometer on the top, electron energy loss spectroscopy. We had no computers except for the EDX machine, the energy dispersive X-ray machine, and I repurposed that without actually destroying it so that we could get digital eels. And I then went ahead and used that with a piece of graphite to get electron energy loss fine structure using the digital acquisition. And I programmed a desktop calculator to FFT it in order to get a radial distribution function. And darn if I didn't get it published in PRL. And IBM was very interesting because they were at a point of time where they were building their own electron beam equipment to do photolithography, electron beam lithography. And they were also building analytical instruments because they had needs that weren't necessarily addressed by the manufacturers. So they were looking for someone for the Watson Research Center who could help develop in both instrumentation and methods that were appropriate for the semiconductor industry. And I remember the point in my interview process where both of us knew that this was the right match. I was asked, can you with this technique locate and characterize a single electronic defect state at the silicon dioxide interface? Very simple thing. But first you have to be able to image the interface to find where the atoms are. Then you have to locate the defect. And then you have to do energy loss in a way that tells you how the carriers could react when it comes nearby that defect. It took me 15 years. We bought a new VG machine. I built a spectrometer for it that was more similar to the Cornell spectrometer, so I knew it would work if I got the details right. And then I began doing the experiment, and it took several years of experiments to understand what it meant to be doing the experiment in a spatially resolved sense rather than in a momentum or angular resolved sense. And that really has, in a nutshell, is what my career has been like. It's been, okay, we've got an instrument. It gives us some hints about what we might be able to get out of it if only it were just a little bit different. You get out the soldering iron and the hammer and go to work and get something that's new. And then the data comes out looking weird.
Mm-hmm.
And it's up to you to convince the community that it's not weird. It's new science, that new ways of things happening that you hadn't thought of. So it's not really new science, but but new combinations of science.
Well, knowing you, I'm almost sure you didn't use a microscope as it arrived, and I'm probably you modified quite a bit from the day you purchased it and the day you got the study of the interface of silicon oxide. So want to tell us about the changes you made to that VG microscope?
Well, it's really 15 years worth of changes, but my focus was always on the energy loss. So I started right away with the design for the spectrometer. And that required understanding the high voltage so that you could build electronics that floated at high voltage, because the spectrometer that I was using was about a 3 centimeter long Wien filter that sits inside of a high voltage electrode to decelerate electrons before analysis. This allows you to to stabilize the energy axis, because the high voltage on the machine isn't flat. It's got an AC on it that's in the VG machine was probably of the order of a half a volt or so. I don't really remember that number. At Cornell, for instance, we got a 60 millivolt resolution in the spectrometer with 15 volts of AC on the high voltage. So that went together pretty well, and the shop at IBM was up to the building, and let's see, and I used digital counting, single electron counting at first. And then there was a period of time that really required me to develop the experimental technique so as to get data which was good enough to convince the world that it was valid, data. There were hard times when the partial photo yield with the synchrotron was showing spectra in the same energy range at the silicon L2-3 edge and at the diamond K edge. And my data were different. They weren't a lot different, but they were different in significant ways. And so I was told to go back and do it again, and I did, and I got the same answers, but no one really understood it. So that required me to sit down at my desk and figure out how to explain it. And so I spent a good 6 months doing the science, the calculations, to show that the core exciton was sensitive to the presence of the relativistic electron. So even though the electron is there for only a few attoseconds at half the speed of light, the charge on the electron was capable of shifting the binding energy of the core exciton and changing the shape of its excited state. And when I realized that and could write it down, I devised a few experiments to show that the data that we obtained was consistent with this model. So that again was in the end, it was a joyful experience.
And all of that knowledge went into the studying that the famous silicon oxide interface?
That happened in more or less the same time. So we got a high resolution pole piece when we bought the machine, and so we were getting about almost a little bit about 3. No, we're getting about 2.5 angstroms there. And then I played with the high voltage. I noticed on the circuit diagrams that there was a high voltage setting on the circuit diagrams that was not on the machine. It was for 120 kilovolts. And I thought to myself, well, if that's on the circuit diagram, they must have intended this to be a 120 kilovolt machine. And it's a little bit of a story, but I knew that Tom Kelly in Wisconsin would ordinarily leave his VG machine in the outgas mode overnight, so that the high voltage would be more stable the next day. And in that condition, the machine is sitting at about 123 kilovolts. So I knew that the machine was designed to do it and could maintain that voltage over a period of time. And so I set up my machine. To operate it at 120. And the change that I needed to make in the basic machine was one resistor at the top. They had put in an extra resistor at the top of the machine reference to derate it so that it would be safer and easier for people to use. And that's why we were using it at 80 kilovolts at Cambridge.
If I'm not mistaken, your VG stand was the only one that was running mostly at 120 kV, wasn't it?
Yes, and I used a lot of tips. I lost a lot of tips operating it that way, but it gave me about 10% improvement on the probe, which was just enough to begin to get images of the silicon lattice and how it transitioned into the SiO2. And that with the spectroscopy that showed a little bit of a ramp below the silicon L23 edge, that was the evidence for the defect state there. And I got a Nature article out of it. Yeah.
Yes, I do remember that paper very much so. And one question I have, Phil, when I met you at the IBM, so your VG microscope had a quite bit of it controlled by computer.
Mm-hmm.
So at which point you modify a microscope to be to have a serious control of the microscope using a computer?
Pretty much at the beginning. I hated having to change the knob settings between imaging and energy loss. And I knew if I wanted things to be reproducible, that there needed to be some kind of way for hardware to know, okay, this is the yield position and this is the imaging position. And so I used what I had learned on the co-op program, actually, how to interface with a computer and in my graduate time. And I knew from my growing period about soldering irons and putting stuff together and making them work, so that it wasn't simple, but it was tedious, but I managed to put the hardware inside the machine that made me able to set the magnification for the imaging, to know the difference between yields and imaging, and to do that control by software, so that I could go reproducibly back and forth between the imaging and the yields mode. And then when the spectrometer came along, I could add that to the scheme. And then ultimately, no, not ultimately. That was the ultimate part of it. Really, was taking the energy loss data in a way that made it reproducible, and then allowed me to do lots and lots of spectra to get the statistics. The beauty of the spectrometer design is that the energy axis is defined by a single power supply that you can work on and make very, very accurate. So from 0 to a kilovolt, I could get the position of a peak to within about 20 millielectron volts. The energy resolution was about 0.2, but the accuracy was very important for the semiconductor community, because if you want to know a band offset, you need to know it to about 100 millivolts. And I could do that with this machine.
Well, a good thing for me was those results with the high accuracy of a core loss edges, like a carbon and silicon, we are still using in our lab to calibrate a yield spectrometer. because we need some reference numbers.
Yeah.
And those results that you had those days are still really good references. If I'm not mistaken, it's also in a book, in a Il's book about the exact numbers.
So that was a lot of satisfaction for me, because this machine still exists. It needs some tender loving care, but I believe it's the only instrument in the world that can do that, that has an energy axis that's that accurate. Not even the neon machines can do it, because it's required that you use an offset supply that's wiggling around with the high voltage, and the high voltage circuitry does not have the resistors are not built well enough to be reproducibly enough to be able to define the high voltage. You can't measure it well enough in order to get the absolute value of the high voltage. The neon system is really very good because it uses at the monochromator slits, it uses the signal off each of the slit sides to stabilize the energy of the electron beam. So it's very, very good at stabilizing a zero loss and getting a very good energy resolution. But the dispersion really depends on the currents in the magnetic sector, and they are not quite good enough to when you go out to 100 volts, knowing whether it's 100.05 or 100.07 of that sort of magnitude. I think maybe with some concerted effort, it could be made so, but it's years worth of work. They're doing an amazing job with the resolution, though. It's and it's been a pleasure to work with their equipment over the years.
Could you tell us about your interaction with Andrei Krivonek and how you end up having a corrector, aberration corrector in your old VG microscope?
Yes, it was obvious to me that 2.2 angstroms or so was not really good enough for IBM's needs, and that we needed a machine that could routinely show atom columns in an annular dark field sense, so that we had not only the periodicities of the atom columns, but their positions near a defect when it wasn't periodic. And you couldn't go to high voltages in order to do this. So there were machines that could see more lattice fringes, but they were very high voltage, and so the samples wouldn't stay in one piece for the semiconductor field. So I knew that Andre and Nicholas were working in Cambridge with funds from the Royal Society, I believe, and they were and that they had some success in making a device that corrected aberrations, but it was in a machine that wasn't capable of supporting the spatial resolution that was needed. So the machine needed to be in a quiet place. Its power supplies needed to be cleaned up. There's a great big electric set of relays in the back of the machine that were at 240 volts AC that needed to be re-energized with DC in my machine in order to create a quiet environment for the electronics. So all of these things needed to be done. At the point that Andre and Nicholas were pretty sure that the aberration corrector worked, they made that known. And I believe the way this worked is that John Silcox wrote a proposal, an NSF proposal for a machine, but it was a little bit of a too big a bite for NSF, because all Andre and Nicholas had was the corrector. They didn't have a whole machine. And so there was the notion that this was really too far out. Well, right about that time, IBM sold patents for laser eye surgery. And that money that coming into IBM was what they call not capital, but expense money, and needed to be spent. And so I wrote a little proposal inside IBM to say, okay, let's get these guys to make an aberration corrector for my machine, and then see if it works. And if it works, we'll have a paper and publicity and a way forward for high resolution. And if it doesn't, we'll know that it doesn't. The lawyers didn't really like it, but they went along. And we did it. So we got 200K, and that set Andre and Nicholas up in their new place of doing work in Kirkland, Washington. And they built a corrector and came to IBM and installed it, and it worked. So we went immediately from 2 angstroms to 0.8.
How easy was it for you to control that corrector at that stage?
Yes, I was already controlling the instrument and the spectrometer using a combination of APL, which stands for A Programming Language, for those of you who are younger than about 60 years old. That was invented at IBM in the late 60s to introduce computers to the physical science community. And it is a language which is rich in characters, which meant there had to a lot of Greek characters, but it has a lot of calculational primitives which are useful for the physical science. Cross products are very easy, for instance. And if you want to go even further, you can do an outer product, which is a basic function needed for what we call Clifford algebra. You'll hear that name again. It just briefly for those interested, the vector algebra is incomplete. There are some operations in vector algebra which give results which are not in the language set of the vector algebra. And among those are the spin matrices, the Pauli spin matrices. So if you want a complete view of the world, you have to have a complete algebra in order to describe it. So anyway, APL does that unbelievably in the 1960s. So I already had a system to control the microscope, and it was a relatively simple operation to add a computer with the digital what Neon calls Dacwin modules that control the power supplies for their systems. And this was relatively simple. It was a 7-layer device, so there were only about 30 lenses, and so I controlled it through APL, which gave me a high-level picture of what I was doing, to their Dacwin software to control the aberration corrector. So it was relatively easy.
Good question I have. What was one of the early results that you got with this now aberration corrected old VG instrument?
The first results were that jumped out at me was with the Gold Island test sample, because at 120 kilovolts with about 100 picoamps, no, actually 300 or 400 picoamps of current, the atoms are readily moving under the beam. So even a 5 nanometer Gold Island has a significant amount of motion, atoms moving around, atoms nearby on the surfaces. So the big change was having the contrast for a single atom be large enough that it stood out against the background of a carbon film. As I spent time looking at these, I could see that there were patterns that were emerging. Particles that were close together would all of a sudden merge, or larger particles would merge under the beams more slowly. There was one example of an FCC, clearly FCC Gold Island that was about 2 nanometers in size, morphed under the electron beam into a decahedral motif that has the 5-fold symmetry, and those. So I spent a fair amount of time talking about that, and it was a discovery period, and I enjoyed that very much. I'm not sure that it has really made an impact on the field, but I think in the future we may, as we get probe sizes even smaller and are able to control their position more accurately, we may find more uses. We might, for instance, make contact with the scanning tunneling microscopy at IBM in Almaden that positioned atoms in particular locations so as to create structures from scratch. And there's some evidence that we might be able to do that with the electron beam under the right circumstances.
Now, I want to ask you about another topic, which is also another big transition point for microscopy community, and your fascination about yields, and then development of a new high energy resolution yields to go with the microscopes. So could you share with us some of your experiences at that early stage of development, higher energy resolution yields, and about advances you helped to get going?
Yeah, this has been a very, very much of a fun project. It coincided with my move to Rutgers from IBM. And that made it in some senses easier because I didn't really have a structure that was confining, but it was also new tasks. Writing a proposal, for instance, I had never had to write a proposal at IBM, so I had 30 years there without having to worry about funds. And and I had ideas that I really would like to explore. I knew that the energy range that they were proposing would allow us to look at phonons. And we with the small probe, we would be looking at phonons with a very different view that we would using angle resolve scattering. So I wrote what amounted to a development proposal with Neon being with Andrei Krivenik being a co-PI, and we got the money based on things that we would like to try to do with it. First of all, see if it worked, and then doing some preliminary experiments in the phonon regime. So that arrived. We got it installed. It's in a quiet room. Magnetic fields are very good. They had to be. And the first thing that we did was just looking at my first experience was actually using it in remote mode. So I took energy loss spectra with milli-eV resolution from my dining room table across the Hudson River.
That should be quite an experience.
Yes, it was. So that was silicon carbide, and it gave beautiful spectra. And they were not the spectra that people are used to seeing because they were not angle resolved. So you have to think in terms of total density of states rather than partial density differential in angle. The angle resolved results are available now using that machine, but they weren't when we got started. So my postdoc, Maureen Lagos, really took the lead on figuring out what was an appropriate first experiment. And he chose MgO because you could make it in the lab. And it formed in perfect cubes. They were small enough to be imaging. We could image. They were about 10 nanometers across, actually. And with our resolution, we could image the atomic columns. We could figure out how good the surface was, and then we could move the probe around, looking at the MgO phonons. It has a 90 millivolt longitudinal optical mode, and it has an acoustic mode that starts at about 40 millielectron volts and goes down, disperses downwards. So all of the elements were there, and we didn't have mapping ability, so Maureen had to take each spectrum separately, and we took a rectangle of a surface and two corners and created a map that showed what they call a Fuchs cleaver mode. So this is a surface mode, surface phonon polariton. And we imaged that to show as a function of energy, how the corners were at a different energy, the face was at a different energy, and the bulk a different energy still. And that was again a lot of fun. It's only the beginning, because because we don't know enough about how the modes are built using the external surfaces of the material. We know more or less, but the details are always mattering.
And have you modified that microscope? So
have we modified it? No, not really. And this is showing a difference between the corporate world, the industrial world, and the academic world. And as you well know, in the academic world, the students should be doing the work. They're the ones that should be learning. And the professor, the PI, should be writing proposals. And boy, that's a high bar for me. So I've done as well as I know how, but I've not done as well as I might have done.
knowing you, I would suspect that you would like to change a few things on the microscope.
Yes, well, so I do have a detector, which is a CMOS detector, and it's very close to being able to be mounted on the end of the spectrometer. The new detectors have a very high dynamic range, and therefore you can take data for a diffraction pattern and know that the zero beam and the high angle beams, which are maybe as much as 5 or 6 orders of magnitude different intensity, can each be recorded accurately. With that information, you can unfold the spatial behavior. You can basically do a Fourier analysis, and you can assign phases to each of the spots so that you can create a real 3-dimensional structure of the material. In the case of energy loss, we also have a large orders of magnitude difference between the zero loss and a core loss, and the plasmons and the phonons. And if we could get those accurately, we can also phase them and do a Fourier transform, which gives us a time domain view of what's happening near the probe. So we have an opportunity for new experiments, which would be the probe mapping the time-resolved behavior of the specimen in space. And that would be wonderful if we could get that done before I finish. It would be very, very much appreciated.
On that topic, I have another question. So knowing you over many years, so you always have some interesting physics problem in your mind that you would like to work on. So, and or often material science problems. So, and a question I have, what are the new scientific problems that kind of make you excited these days that you would like to go and deal with?
Yeah, we from the very beginning in the 50s, when Rufus Ritchie did the theory for electron energy loss scattering of plasmons, we have made the approximation that the electron does not change its velocity when it scatters. So admittedly, it's a 50 or 60 kilovolt electron, and we're looking at specimen excitations that are sort of 0.1 eV out to, say, a kilovolt. So there's not a big change in the electron. But if we look at it on the nanoscale, when we try to calculate what's happening in the specimen for the close approach of an electron within a couple of angstroms of the surface of a 2 to 5 nanometer particle, the electromagnetic field imposed by the electron within the confines of that object, of the surface, varies by a huge amount. And we have used what we call retardation to understand delays in behavior of what we see in the specimen. But these are really gross approximations. So what you really need to do is you need to write the electron scattering problem in terms of relativity. It needs to be what they call Lorentz invariant in doing the boundary conditions and the applied and response fields within the confines of relativity. It turns out that we understand how to do this, and we have very tantalizing intuition that it's not very different from what the eventual gravitational theory would look like on a cosmic scale, length scale. So we have what I think is a very exciting opportunity to help in the task of unifying electricity, magnetism, and gravity into one theoretical field. There are others that are beginning to do that. They're thinking about how to do that at Rutgers now. It involves this weird algebra called Clifford algebra, but it will simplify and make more robust our understanding of both black holes on a cosmic length scale and nanoscale particles and defects on the atomic length scale. And I think that's pretty cool.
It is indeed. That sounds fun. And you want to try some experiments on a microscope to get some of these issues sorted?
Oh, that's a good question. Well, the things that I have thought of that would be easiest to do at the beginning is given a high dynamic range detector is to do the energy loss from a millivolt to a kilovolt. This requires thinking about how do you take the data, because if you want to do a reasonable Fourier transform over that energy range, where you get the structure of the phonons and the structure of the core losses together, you need upwards of a few million data points.
Wow.
So yeah, so what you can do is that the structure varies logarithmically. So you learn how to take the data in a logarithmic fashion, and then you can fix it up later. You can do interpolations, and you can enforce basic physics that you believe might be true like causality. But one perhaps ought to realize that our notions of causality may not be entirely accurate yet. We don't know enough about space and time and how it behaves. A good example of this is what we call the holographic theory of space-time, which posits that what we see within a volume of space-time is not what's actually there, but the behavior which is forced by behavior on a surface which bounds that volume. And this notion is only about, I think, 10 or 11 years old, but it's getting more and more serious looks as we find out more about it. It is really astonishing to me that a nanoscale scattering experiment looking at surface plasmons, the theory of how light and information is exchanged with the surface of a black hole, and error correction in quantum computing could have a common mathematical foundation. And I just think, if I were to die tomorrow, just knowing that would be enough.